Okay, so when it comes to kinetics, this is like a whole different world of chemistry to us. Now, it's very, very different. I always say this is the great introduction to 229, those of you who are taking 229, because this is a lot like what 229 is. It's just so different than what you've seen before. I liken it to like if you've taken pre-calculus and then you take calculus and you're like, what? Well, I don't understand how that had anything to do with each other. That's sort of kind of how I feel like with 219 and 229, because the chemistry changes so different. The chemistry just so drastically. So this is kind of our first experience in that. And this is chemical kinetics. And kinetics is what we're going to be looking at, is we're going to be looking at the speed of the reactions. So how fast the reactions go from reactants to products. And so we're going to talk about how we can control the speed of the reaction. And we're going to be doing an experiment with this probably 2 weeks from now. We'll be ready to do that. Okay. I think, let me just make sure this is being recorded. Yeah, it is being recorded now. Okay. Okay, so how we do reaction rates. And if you don't have a calculator, you need to make sure you have a calculator, a phone, something that can calculate simple things here, because it's going to be really important that that I'm going to tell you some things, but you need to prove to yourself what I'm telling you is true, because it can be a little tricky. Okay, so the rate, again, is how much it changes over time. So it's just the same thing as like when we drive our car, right? It's the speed over a period of time. So it's the change in distance over change in time. That's what we do with speed. And so that's why we have miles per hour. So when we do kinetics, we're just going to do the speed of the reaction rate. And the speed of the reaction rate is going to be the change in concentration over change in time. Remember, concentration is molarity. So it's the change in the concentration. Remember, these brackets mean molarity. So whenever you see a bracket, like if you have like 1.4, this means 1.4 molar, right? And remember, molarity is moles over liters. And so whenever you see that, that's what this means. And over time, in kinetics, we always use seconds. So now, if we look at the rate a reaction goes from reactants to products, we're going to increase the amount of products. So if we look at the rate with regards to products, the rate will be positive. But if we look at with regards to reactants, the reactants are disappearing. And so we're always going to be putting a negative sign if we're looking at the rate with regards to the reactants, because the reactants are decreasing. Now, the rate of an equation will be the same no matter what we're looking at. If we're looking at it with regards to any reactant or a product, it needs to be constant. So we're adding this negative here to correct the reactant, to correct the rate according to our reactants. Now, this is going to make a little bit more sense when we go to the next slide. Okay, so on the left, we have a reaction with a fast rate. On the right, a slow rate. And now we're going to look at how we actually calculate the rates of these reactions. Now, in kinetics, we're going to learn 3 different ways to do the rates of the reaction. We're not going to mix them each day, but it's important, and you'll see I'm going to continually draw parallels to each of them to help you kind of try to keep it separate in your brain. Okay. So the first one, we have at time equals 0. So here's our A. We have 8 of them, right? 1, 2, 3, 4, 5, 6, 7, 8. And B, we have 1, 2, 3, 4, 5, 6, 7, 8. And C, we don't have any. Here's the same exact thing, and this one's going to be our slow rate. So we have our fast rate and our slow rate. Now we're going to look at, so now if we look at our first one, now our A has gone down, so it was at 8, now it's at 4. Our B was at 8, now it's at 4. C was at 0, now it's at 4. Now, if we look over here at our slow, we started at 8, 8, and 0. This only went down by 1, and up by 1. So now we're going to look at how we calculate these rates. And again, this is just a really simple example. So if we want to look at the rate, and so this means the rate with regards to C being the product. So we would often say that this is the rate with regards to the product. It's going to be a positive sign, right? Because we're forming product. So it's going to be, our rates are always positive, but that's why we don't have a negative in front of here. So we ended at 0. We ended at 4. We started at 0. So 4 minus 0, and our time is 16 minus 0. So our rate is 0.25. Now, let me go back. So remember, this is with regards to our product. So now we're going to look at it with regards to a reactant. So now if we look at the rate with regards to reactant A, so we're looking at how A changes over time. Well, A ended at 4, it started at 8. So 4 minus 8, again, the time ended at 16, started at 0. But we have to put this negative sign here to correct, because our rates number 1 are always positive. Because if the rate was 0, that just means there's no change, right? So rates are always positive, so we have to correct for this, hence the negative sign. So whenever you're looking at a rate with regards to a reactant, you're always going to put this negative sign in here to correct for the fact that the reactants are disappearing. Okay, so now let's look at our slow. So here's our slow. If we look at this again with regards to our product, it was at 1, 0, 1 minus 0, and our time 16 minus 0. Our rate is much slower. So our rate is 0.25. And again, this would be molarity per second, and this would be molarity per second, because our time is in seconds, and our concentrations would be molarities. Okay, so now we're going to go a little bit quicker, but I want to make sure that you understand this, because we're going to go to some more complicated examples in just a minute. Here is the next one with regards to a reactant, right? X is a reactant, therefore we need a negative sign here. We look at the change of X, 7 minus 8, and then our time was 16 minus 0. And again, it's the exact same rate. We had to put that negative sign in there because the rate of a reaction, you can express the rate of a reaction with regards to any reactant or product, and it should be the same. Hence why we have to use that negative sign. Okay, so we're going to go a little quicker. So here's time equals 16 to time equals 32. And again, to figure out the rates of our reaction, you can see our rate has now changed. Now it is at 0.125 because if we look at C, 6 minus 4, and then 32 minus 6, the rate of our reaction is 0.125. Okay, if we look at our next one, we have 2 minus 1 over 32 minus 16, 0.0625. And again, now we're gonna go quickly here so you can see this because you kind of get the gist of it. And you're gonna see, here it is our rate again. Here's with regards to our product, 8 minus 6 over 48 minus 32, 0.125. Again, with regards to A, now we have a negative sign because again, A is a reactant, right? 0 minus 2 and then 48 minus 2, 0.125. The rate is exactly the same. Same thing when we look at our slow reaction, the rate is the same if it's regards to a product or a reactant. And again, that's why we put this negative here. Okay, so now we're gonna look, we're not quite ready for a real reaction yet, but let's just say we have a very simple reaction that goes from red to blue. So you're gonna see the number will always stay consistent, right? Because we always have the same number of molecules, right? Law of conservation of mass, right, is neither created nor destroyed. So 84 plus 16, that equals 100, 71 plus 29. It's always going to equal 100. And we're just looking at the rate of change when it goes from 0 to 50 seconds. So in this reaction, one red molecule turns into one blue molecule. The number of molecules is always going to equal 100. And the rate of the reaction can be measured as either the speed of the loss of red or the speed of the gain of blue. So we can look at it as the decrease of red or the increase of blue. So all I did here was graph exactly what you saw. So I just graphed, let's go back. I just graphed red going down and blue going up with time on our axis. And so you can see here is our reaction with regards to product. Our product is increasing and our reactant is decreasing. Now here is the rate of the reaction. So we're going to talk about how we got this. So I just did a bunch of calculations. We're going to talk about this in great detail in a little while. But you can see that as the reaction goes to completion, which the completion, we'll talk about that when we get to equilibrium, but that's 229. It slows down. So it's faster at the beginning and it slows down at the end. And we're going to talk all about the mechanics of how and why that happens. Okay, so now let's look at this rate changes over time. So as time goes on, the rate slows down, and we're going to talk about how the concentration of the reactants decrease. Because if you are at the beginning of your reaction, you have a lot of reactant molecules, right? So we have 184, 71. So their ability to react is greater because they're going to come in contact more often. When you get to the lower end of your reaction, you don't have as many reactant particles, so it's going to be harder for them to interact, and therefore the reaction is going to slow down. So as we go through our reaction, it slows down until it hits equilibrium. And now we're not going to talk about equilibrium. Equilibrium is a whole nother world, and that's what we spend about 70% of the time in Chem 229 talking about. So at some time the reaction stops, either because we run out of reactants or we reach what's called equilibrium. Okay, so now we're going to look at the reaction rate in stoichiometry. So in most reactions, the coefficients of the balanced chemical reactions are not the same, right? So this is like a 1, a 1, and a 2. And so for these reactions, the change in the number of molecules of one substance is a multiple of the other. Okay, so what does this mean? And this becomes very important when we're talking about kinetics. And so for every 1 mole of H2, we use 1 mole of I2 and we make 2 moles of I, right? So we've known this for like over a year plus more. So therefore, when we're looking at rates, remember the rate, we can show the rate for the reaction with regards to either H2 or I2 or HI. Therefore, we need to correct for the stoichiometry of the reaction. This is a 1, this is a 1, this is a 2. So therefore, to be consistent, we need to multiply the rate by 1 over the coefficient. So whenever we're looking at the rate with regards to HI, we're going to have to divide that rate in half so it is reflected from the rate of the whole reaction. And so when we do this, and again, when we're doing kinetics, you're probably going to come up with a lot of questions. Ask them, because if you have a question, there's probably 10 other people who have the exact same question, because this is going to be very different than what we've done before. So to figure out our reaction rate, the rate is going to be, so if we look at this, this is a reactant, reactant product. So our reactants will be negative, right? Because they're disappearing. So we need to correct for that negative because remember, rates are always positive. So we put a negative sign and you're going to see why we do this in just a second. You're going to see. So this is a 1. So it's just the change in. So this means change in the concentration of, remember, this means molarity. So molarity over the change in time. Again, this is seconds. So this will be the same as the change in H2 over T time, the change in, and that will be the same rate as if we expressed it with regards to I2, which again has a coefficient of 1, and that will be the same as the coefficient of HI. But HI is a product, so products are increasing, so this will be a positive number, 1/2, because remember, all of these are equal to each other. They all have the same rate. We can express this rate with regards to H2, I2, or HI. It will be the same number. And so therefore we need to correct for having this coefficient of 2, so we multiply it by 1/2. Okay, so I'm trying to go really slow, and the reason we're introducing kinetics now instead of next week is because it takes a little while in your brain to shift, and I want you to be able to see this now, so when we do this next week, you're going to be more able to understand how all of these things work. So we're going to first talk about average rates. And again, we're going to learn how to calculate rates in many different ways. So the average rate is the change in the measured concentration over any particular time period. And it's just going to be a linear approximation of a curve. The larger the time interval, the more the average rate deviates from the actual, what we call instantaneous rate, which we're going to learn how to calculate that also. Okay, so now here's where you need your calculator because you need to prove to yourself what I'm doing is true. Okay, so remember, if we're looking at red to blue, if we want to look at the rate with respect to red, so if we look at, for example, these first 5 seconds, red goes from 84, so it was 84 minus 100, that's our change in red, and our time was 5 minus 0. So if you put that in your calculator, 84 minus 100 divided by 5, you get negative 3.2. Again, this is a reactant. So we have to put a negative here to make sure our rate is always positive. And here is our rate after 3.2 seconds. Now, we're going to do the next one so you can see how this works. So the next one, we got 2.6. That's going to be the difference between 71 minus 84 over 10 minus 5. 71 minus 84. And you get, again, you have to put a negative and you get 2.6. Now, if we look at this, these are, again, our average rates. This one here is going to be the difference between 0 to 10. So in this case, if we're looking at with regards to red, it would be 71 minus 100, and now our time is 10 minus 0. And so when we do that, we get 2.9, again, putting a negative. Now, again, this is how we got all of these numbers, and you're going to learn how to do these numbers with actual equations, but it's important that you understand how we're doing this. So remember, it's the change in the concentration of some molarity over the change in time. And if you're looking at a reactant, you put a negative in front of it. If you're looking at a product, you put a positive in front of it. If there's a coefficient, it's 1 over the coefficient. Okay, so now we're going to look at actual concentrations. So here's our H2, our I2, and our HI. So at the top, you have the balanced chemical equation. And remember, there's 2 HI, so we need to correct for it. So if we want to look at the average rate, remembering that rate is the change in H over time, the stoichiometry tells us that for every 1 mole of H, 2 moles of HI are made. Assuming that a 1 liter container at 10 seconds, so here's our time, 10 to 0, we used 1.81 moles of H2, right? So we started, and this again is going to be where you're going to prove this with the calculator so you understand what I'm doing here. We started with 1 molarity, and after 10 seconds, we had 0.89. So 1 minus, actually we should do it the other way to be technical because it's a reactant. 8.819 minus 1 over, well, we're not going to do our rate yet. We're going to talk about how we got HI. So if you do this, you get 1.81 moles. And again, I just put my negative sign in there. And so you get 0.181 moles of H2. Now, if we used 0.181 moles of H2, remember for every 1 mole of H2, we make 2 moles of HI. That means if we want to look at our concentration of HI, we're going to double it. And yes, can you guys see the writing?
No.
Oh.
No, this whole time you can't see my writing?
No.
I'm
I
sure.
thought that was like the calculator quacking away.
Hold on 1 second. I don't know why it's not working. It's so weird. Hold on a second. Let me figure out why. Can you see now? Well, sorry, you can see my screen, but you can't see my writing. Because this is going to become really important in a second. We're right here. Okay, can you see can you see now?
Yeah.
Can you see the writing? Can you see that I'm writing right now?
Yep.
Okay, good. Okay, good. Okay, so I'm going to go back here because this again is going to become really confusing in a second. Okay, so if we have, so we're just going to assume that we've got 1 liter, and I'm going to call these moles now. So if we start with 1 mole of H2, and after 10 seconds we have 0.819, that means we have 1 minus 0.819, which is 0.181 moles of H2. So if we used 0.81 moles of H2, that means that because of the stoichiometry coefficient, there's 2 HIs. So that means that how much HI did we make? We made 2 times that amount. So we actually made 0.362 moles of HI in the first 10 seconds. At 60 seconds, so if we look down here, all we have left, so you're going to see when we do this in lab, we're going to measure the change in the disappearance of one, and that should be this exact same as the change in the appearance of the other. So we only have 0.301 moles of H2, but we started with 1. So that means we have 1 minus 0.301 moles. And if you put that in your calculator, 1 minus 0.301 moles, that means we used 0.699 moles. So that's how much we used up. And so if we use 0.699 moles, again, it's a 1 mole to 2 mole ratio. So if we multiply that by 2, that means at 60 seconds, we've actually made 1.39 moles of our HI. And that is going to become very important because remember these two numbers. So at 10 seconds, we had 0.362 moles, and at 60 seconds, we calculated 1.398 moles. Here's how I got all those numbers. So what you do is you put this in a spreadsheet and you calculate one and you just drag it down on Excel, which we'll be using Excel later in the semester. Okay, so that's how I got all these numbers. So here's that 0.362. Again, I just subtracted these and then I multiplied it by 2 because HI I have to multiply by 2 to get the concentrations. Okay, so that's just the concentrations of HI. I want to know the rates. So if I want to do my rate with respect to H2, again, the rate should be the same as it is with HI. I just have to correct for it. So if I look at my rate in the first 10 seconds, the change in my concentration, so the change in my concentration rate was 0.819 minus 1. That was my change in my concentration over the change in time, 10 minus 0. When we do that, so that's the change in the concentration over the change in time. That's supposed to be a bracket. You get negative 0.0181 in its molarity per second. But again, we need to change that to a positive because reactants are disappearing. And again, our rates are always going to be positive, so we have to correct it with a negative. So let's look at the exact thing with regards to HI. So if we look at this, so right now we'll look at HI in a second. So how I got all these numbers is we subtracted one from the other. So if we look at, for example, the next one, 0.819. So if we look at how we got this number here, it's this time frame that we looked at, right? And so I just took 0.819 minus 0.670. Should be backwards, and then I divided it by 10. I just know that my rate always has to be positive, so however you subtract it, as long as you know it's positive, you're good. I just always think absolute value when I do these. Kind of like when we do error analysis, sort of think of it as the exact same way. Okay, so let's look at how we got, and we're going to do this in a second. How did we get, let's look at this exact same one right here. But let's look at with respect to HI. Remember, the rate should be the exact same. So if we look at HI, so HI was, and again, we'll look at the same thing here, 0.660 minus 0.362 over 10. But when we do this, I got 0.0, let me fix that, 0.298. Okay, what did I do wrong? You can see what I did wrong. I should get this number.
You forgot the 1/2.
Exactly. Yeah, remember it's 1/2, right? So if you divide that by 2, you get this number. So that's going to be really important that you remember those stoichiometric coefficients, because they're going to pop in here and there and everywhere. But that's only, and this is very, very important, this is only when we are doing average rates. This only applies to average rates only. It does not apply to all the other different ways we're going to learn how to do rates. Okay, so if we look at this, Here it is. I just, again, calculated all of the HIs. I did the exact same process. I just remembered I had to divide them by 2. And so that's how we got all of these rates. And if you see this, the rates are exactly the same because, again, we can express rates with regards to any reaction, any reactant or product in a reaction, any reactant or product, it should be the same. And we're looking that, look at here it is, 0.2 all the way down to 0.003, our rate did decrease. Now, go ahead.
So for that first one, did we divide or did we turn it by 1/2? The first one.
Hold on. This right here?
Yeah.
Yeah. So when we did the first one, so we were just looking, we'd be looking here. So it would be 0. Get rid of all this. 362 minus 0 over 10 minus 0, but we need to multiply by 1/2. Mm-hmm. 362 divided by 10 divided by 2.
So say HI, let's say it made, just hypothetically, 3 moles of HI. Then would that coefficient be 1/3?
Yes.
Like to multiply by? Okay. So basically just whatever the
yeah, whatever your coefficient is, you multiply by 1/2 of it. Or by 1 over it. So if this was a 4, you would multiply this by 1/4. Okay. And same thing with the reactants. If you had like a 2 here, you would multiply it by 1/2. And just don't forget your negative sign for your reactants.
Oh, so that goes for products and reactants.
Products and reactants. Yeah, whenever you've got a coefficient, it's 1 over it. Because we want to make sure, because those rates need to be the same, we have to correct for the coefficients. If we don't, then the rates wouldn't end up being the same.
So for reacting is multiply, and then for product is divide? Or like 1/2 or 1 over the mole?
It's always 1 over the coefficient, no matter if it's a reactant or a product.
Okay.
Yeah, 1 over the coefficient. Okay, so when we're looking at this, and we're going to start taking a very molecular view when we're talking about kinetics. And again, those of you taking 229 will always be doing a molecular view. If we look at this rate here, it's much faster than this rate down here. And the reason is because when we start a reaction, you can look at our concentration. Look at how much H2 we have in our reactants at the beginning versus how much H2 we have in the end. We don't have as much H2. In order for H2 and I2 to combine to make HI, they have to hit each other somehow, right? Somehow they have to hit each other. If there's less reactants available, it's going to be harder for them to find each other. Therefore, their ability to react, which we're going to talk about what does this actually mean to react later, to actually form this product is going to be slower. And that's why the rate of a reaction slows as we go. And eventually it will hit equilibrium. So eventually what happens, so what we're doing right now in kinetics, we're just measuring this rate of change, but eventually this rate will just be the same again and again and again. It'll always be the same. It'll reach equilibrium where it won't change at all. And again, that's what we start with 229 is on our equilibrium. Okay, so all I plotted here, hold on, what just happened again? Oh, it disappeared again. You didn't see it. Okay, so all I plotted here, so, great question. Will it ever hit 0? No, it never hits 0. It approaches 0. So those of you who have had calculus, you remember limits? Like, unfortunately, this kinetics is actually calculus. We're just not doing the calculus part of it. We're looking at the solutions. This will, it could infinitesimally get to 0, but technically never get to 0. So the rate actually never goes to 0. It approaches the limit of 0, but never reaches it. Okay, so what I have here is I just plotted the time versus concentration. So again, I want to remind you that we are doing average rates. So the average rate in a given time period equals the negative slope of the line connecting the point, and the positive slope for products, negative slope for reactants. And you're probably like, what? So let's look at this. So what we're going to look at, and we're going to calculate this in a second, we're going to look at the negative slope of our reactant. And the reason it has to be the negative slope, because if we took the slope of this line, it would be negative. But remember, rates are always positive, so we take the negative of the slope. So we take the negative of the slope to give us our positive rate. And here it's increasing anyway, so we'd have a positive slope no matter what. And so when we did this, because remember slope, right? Change in x over change in y. Same thing here. This is literally what we did on our last slide. We just did the change in x over change in y, right? So we did the change in our concentration over our change in time. So what we were doing is we were finding our slope. So when we did that with regards to our first 10 seconds, we got 0.0181 molarity per second. Now, if we looked at the change, and our time change is going to be from 0 to 40 seconds. Do you see how the slope of our line is deviating from the actual concentration? So the actual change in the concentration when we had our slope for 10 seconds was pretty close, but this is deviating. This line here is deviating from our actual concentration, our change in concentration. So it's not going to be as accurate when we go over longer time periods. So if we did the first 40 seconds, we got 0.0150. So we can still do it. It's just not really as accurate or as reflective as it should be. And again, if we even go over our further, if we do the slope, again, what we're doing here, you just go back. What we're doing is we're looking at, so what we're doing instead of going from like 0 to 10 seconds, if we calculated a difference and we went from 0 and we didn't look at it again until 40 seconds, we would be looking at these numbers here, and our rates would be much different than they would be if we looked at it before. So if we look at, let's just do H2 because it's easier. So we'd have 0.449 minus 1 over 40, and then the positive of it. 1 minus 0.449 divided by 40. So I got the same exact number. So I got 0.015 about, which is much different than our other numbers are. So it's not as accurate. You can still do it though. So if we did it from 0 to 80 seconds, and so what we're doing here is, so when we're going to do this in lab, very similar question. So we're going to do a very similar problem like this in lab, and we're going to try and figure out at what point do we need to check our concentrations. So at what point are we going to record our concentrations? And depending on the longer amount of time we go between reading them, depending if it's a fast or slow reaction, the different we're going to have in our accuracy of our answers. Okay, so now we're going to look at instantaneous rate versus what we just looked at was average rate. Okay, so I need to go back here. So the average rate, right, is the change of x and the change of y. We're going to go back because this is, again, why we're introducing this now, because your brains are going to need some time to absorb what we're about to talk about. So we did average rate. Average rate is the change, right? Change in our x. This is the change in our concentration over the change in time. Right? So it's just like we did with our slopes, right? Change in x over change in time. Now we're going to do instantaneous rates. Instantaneous rates is the actual concentration at any particular point in a time. It is the slope of the curve. So do you remember tangent lines? So what we're going to do now is we're looking at this specific rate at a specific time. What we were doing is we were looking at the difference between one point and another point. And that was what we were doing, our average rate between the two. Now we're going to do an instantaneous rate. I want to know the rate right here. I don't want to know the difference. I don't want to know the slope. I want to know that rate at this specific time. So at 90 seconds, what is the rate? This is a different way of finding rates. This is going to be instantaneous rates. Okay, so instantaneous rates are really annoying. We don't do these too much because you have to have a graph when you're going to do your instantaneous rate. So an instantaneous rate, remember, is at a specific time. And so if I want to know at 50 seconds, so here's 50 seconds. So I go up. And if I want to do H2, H2 should be the one that's decreasing because it's a reactant. So here it is. Here's my H2. Here is at 50 seconds. I want to know what is the rate at this point in time. So now I take, remember, slope of the tangent line. So this is the tangent line. That's the tangent line. And now I'm going to take the slope of the tangent line. And again, you can only do these if you see the graph because you have to be able to take a slope of a tangent line. And so I look at the change of this. So the difference between here and here. So this change in my molarity is 0.28 molar. And then I look at the time, and that's 40 seconds. So it's like 30 seconds to 70 seconds. And that's 40 seconds. So here's my change in my concentration over time. My instantaneous rate at 50 seconds is 0.0070 molarity per second. Now I'm going to go back. So this is at 50 seconds. We're going to see the difference, which is going to take me a while. So if we looked here at 50 seconds, we got our average rate was 0.0081. So it was not the same. And that was just measuring over 5 seconds. So there's a difference in our rate. Our instantaneous rate is going to be more precise than our average rates. Although instantaneous rates are super annoying, so we try not to do them very often. But the instantaneous rate is the slope of a tangent line. Now, if we want to look at, so let's go at 50 seconds again, but this time, let's look at HI. So if at HI, here again, we try to draw a slope of our tangent line. Once you do this, you definitely need a ruler. So you look at the difference. So we look at our concentration difference and subtracted that. We get 0.56 molar. 0.56 molar. And if we look at, again, 30 to 70 seconds, right, because this is the same, 70 minus 30 is 40 seconds. But we have to correct for the fact that there's a 2 here. So we do a 1/2, and we get the exact same instantaneous rate. Okay, so those are instantaneous rates. Okay, so let's go and do some average rates, because again, instantaneous rates we can only do if we actually have a graph, and we don't have a graph here. So these are the problems that we're actually going to see in the very, very beginning of our problems. So for the reaction above, the change in I goes from 1 molar to 0.868 molar in, 10 seconds. Calculate the average rate in the first 10 seconds and the change in the concentration of H. So this is what I mean by very different, because usually we would think, oh, they're giving us I's and asking us for H's, we have to do a mole ratio. No, there are no mole ratios in kinetics. Those no longer exist. There's also no stoichiometry, I guess there's a tiny bit of stoichiometry, but a tiny bit, just molarity. Okay, so remember, it's change in concentration over change in time. Well, our time, they're telling us, is 10 seconds. So if our time is 10 seconds, now we just need to figure out the change in our concentration. Oh, right here. And this is I. I's got a 3 in front of it, and it's a reactant. So therefore, because it has a 3 in front of it, and it's a reactant, I'm going to put a -1/3 in the front of it. Because I have to correct for the coefficient and correct for the fact that it is a reactant, hence why that negative sign is there. And then I'm going to just 0.868 minus 1 molar. So if we plug that in, we get, okay, I just put that a little too low. Here it is much neater, much nicer, exactly what I just wrote. The 3 to correct for the fact that there's a 3 here, the negative to correct for the fact that it's a reactant, and then I just subtract. Time, change in concentration. Easy peasy. But that gave us the average rate. We also need to figure out the concentration of H+. So remember, whatever rate you get, that is the rate with respect to anything. That is the rate respect to this, with respect to this, respect to this, respect to this, respect to this. Remember, because the rate is the same with respect to any reactant or product in a reaction. So if we want the rate with respect to H+, well, let's write it. So the rate with respect to H+, the rate equals, it's H+, so it's 1/2. It's a reactant, negative. The change in H+ over change in H+ over change in time. Right? Well, we don't have H+, but remember the rate is the same. So the rate of this is 4.40 times 10 to the -3. And again, it's molarity over seconds, concentration over time, equals -1/2 change in A+ over change in time. And so the units of this will be molarity per second, right? That's the change that we're going to look at in this per time. And so all we need to do is we just need to multiply this by -2, right? And it should work out. So again, I have all that much neater here. So we wrote this was our rate. Oops. This is our rate with respect to H+. And so we just multiplied it by -2 times our rate. And we got, that's our rate with respect to H+, because it's a negative, because it's a reactant, right? And so we would expect that the concentration over time of H+ should decrease, hence the negative sign. Now, when you're doing kinetics, you just need to remember that it's negative, it's a reactant, and it's a positive, it's a product. If you forget or mistake these negatives, check your answer in the end and make sure it's true, right? Because now this, a lot of times people are like, I thought it couldn't be negative. This is not a rate, not a rate, right? This can be negative. This is the change in concentration. Remember when we were doing like the change in molarity over change in time with our simple numbers before it? This number could totally be negative. Not a problem if that number is negative. So if we were going to write, for example, with respect to water, the rate with respect to water, we could find out the exact same thing. It would just be plus 1/2 change in water over change in time. So you can write this for any of them. Okay. So I want you to try this one, and then we're going to go over this together. This is going to be a little tricky, so try and see if you can figure out this one. So they're giving us grams of NOBR, and of course we'll give you the molar mass now, giving you a volume and a time. We want to know the average rate of BR, and again, molarities per second. So we're looking for the average rate of this. So I'm going to give you a minute to try and start this, and then we're going to go over it. Hold on, I'm going back to it. Okay, so let's go over this. So the first thing that we need to know is that average rate has to do with concentrations. Well, we don't have a concentration, so we need to make a concentration. Well, we have a grams and a milliliters, get a concentration there, right? So 2.4 times 10 to the 2 grams of NOBr, molar mass given, 109.91 grams in 1 mole NOBr. That gives us our moles. I don't know what that is. But then we have our liters, and we can get to molarity, right? So let's say we got to molarity. Divide by liters equals molarity NOBr. Now they ask for Br2, right? So we have a time and a concentration. So I'm just going to go so you can see, or we could have, right? Could have just gone to Br2 here. It doesn't matter, right? Because our rate's going to be the same with respect to whichever one. So if we do this, so first thing I'm going to do, let's get to our molarity so we can actually see this. I actually did go to Br2 here, which again, doesn't really matter because you can figure out both. Okay, so when we do this, we get our moles, and we went to Br2, and we just divide it to get to our molarity. There, now we've got our molarity. And so if we want to know the average rate, by the way, this needs to be in seconds. Remember, I told you earlier this had to be in seconds, so don't forget to turn this into seconds. And we're looking for the average rate. And remember, our rates, when we're doing average rates, are always molarity per second. I want to specify this. For average rates only, it is in molarity per second. I also want to specify average rates are the only ones when we look at these coefficients of these equations. So when we do this, now all that was old. And so our new piece here is our rate of change of Br. There's one coefficient. I mean, there's a 1, so we don't have to do anything. It's positive, so it's going to be positive. So if we would have gone with NOBr2, we could have done the same thing. We just had her done -1/2 of our concentration, and we would have got the exact same thing. So if you, and some people might have gone to NOBR and then converted it to BR, your answer would have been negative one half your concentration, and you would have ended up with the exact same rate. So we do there, so 5.54. Okay. So that's just an example of how we do, and I want to be, again, very specific, average rates only. We are going to be doing so many different types of rates. I need to make sure that we've got in our brains that average rate is the change in one over the change in the other while looking at the balanced chemical equation. This will be the only time we use the balanced chemical equation to figure out rates. So in your brain, you need to put average rate, units, molarity, seconds, use coefficients only. This is the only time we're ever going to do that. Okay, so that again is average rates. It's very different than instantaneous rate. Remember, an instantaneous rate, the slope of the line, we're going to be doing reaction orders and experimental determinations also, and those have nothing to do with coefficients, and those units are very rarely molarity per second. Okay, so how do we measure reaction rates? So we have to be able to measure the concentration, at least something, and at many points in time. And so we could do this by continuous monitoring, or we can do this through a sample called quenching where we can kind of stop it. But no matter what, we have to just be able to figure out, and this is what we're going to be doing in the lab, we need to be able to measure the concentration at many points in time. And so in lab, that's exactly what we're going to be doing. We're just going to be measuring the concentration at all different points in time. Okay, so factors that are going to affect our reaction rate. So the nature of the reactants, what does that mean? So smaller molecules will react faster than larger molecules, right? Because if the molecules are smaller, right, their surface area is smaller, so it's going to be easier for them to meet in the correct orientation. So it's very important, and we're going to talk about this a lot. Two things have to occur for a reaction to happen. They have to have enough energy to react, and they have to have the right orientation to react, right? So think if we have two molecules and they approach each other at the slowest possible rate, all that's going to happen is they're going to meet each other and then just bounce off, right? Because they don't have enough energy. Or if you have a molecule, let's say you have one molecule that looks like a half moon and the other one that looks like a circle, right? The only way they can react is if they meet each other like this. If they meet each other like this, nothing's going to happen, right? So they have to have the right orientation and the right energy. So they can hit each other as fast as they want this way. Nothing's going to happen because they're not in the right orientation. So smaller molecules will tend to react faster because they're more likely to be in that right orientation. So gases tend to react faster than liquids. Again, gases move quicker, right? So therefore they're more likely to have enough energy to collide with each other. Powdered solids are more reactive than blocks, again, because there's more surface area for them to hit each other. And then certain metals are more reactive than others, and we'll talk more about this. And then ions tend to react faster than molecular compounds because ions, we don't have to break those molecular bonds. Okay, so how do we affect reaction rates? So temperature can affect reaction rates. And we're actually going to do this a bunch when we're in class. We're going to actually change these reaction rates and temperature. So a rule of thumb, for each 10 degrees Celsius, the speed doubles. So increase by 10 degrees, increase your reaction by 2 times. So your rate will go up it'll double. And so we're going to look at this, but not today, of how we're going to actually calculate these things, but we're not going to do that today. So the next thing is catalysts. So what is a catalyst? So you hopefully learned this in biology. They're substances that react without being consumed. So they participate in the reaction and then they're regenerated at the end. And so they come back at the end, and we're going to talk a lot about catalysts. So there's different types of catalysts. We have homogeneous catalysts. It means the same phase, like a gas reacting with a gas. That would be a homogeneous. Heterogeneous, that a different phase, like a gas and a solid. That would be like a heterogeneous, different phases. And we're going to talk a lot about how these catalysts work later. Now, the other thing we're going to talk about is reactant concentration. So generally the larger, So generally the larger the concentration, the faster the reaction. Because if you have greater concentration, and we've been talking about this, they're closer to each other. And if they are closer to each other, they're more likely going to have the correct orientation and the correct energy because they're going to be closer to each other. So gases depend on pressure. If you have a higher pressure, you have a higher concentration. And then with aqueous solutions, it's a solute to solution. It's the molarity, right? Higher molarity, faster reactions, tends to be. Okay, so we're going to look very quickly at a very important piece. And so this is going to be important for now and for all chemistry. This is what's called a reaction profile. So this is the reaction progressing, and this is energy increasing. So if you have your reactants here and your products here, and I'm going to give these numbers, energy, I'm going to call this one 10. I'm going to call this one 20, right? And we'll talk about what these units are here. So if we look at the energy of our products at the end versus the beginning, you can see that our products now have less energy. And so that means our energy was released. Energy was released. This is an exothermic reaction. Energy is released. So if I was going to write this here, I would write heat here. I would treat heat as a product. So this is an exothermic reaction. Now this activation energy is going to become incredibly important. So in order for this reaction to occur, 2 hydrogens have to hit 1 oxygen molecule in the correct orientation with the correct amount of energy to make 2 water molecules. So it's going to take this right here. This is our activation energy. This is the energy it takes to make sure that we've got our right orientation and our right energy. And so that this is every reaction has this. The smaller this is, the faster the reaction is. So if you had, let's say you just had 2 molecules and they were circles and they came together like that. So if they're both circles, their orientation doesn't matter how they hit each other. They're both circles. It doesn't matter. So their reaction profile might look like, so here's the reactants, and there's our products. Their activation energy is very small, which means this is going to be a very fast reaction. So the smaller the activation energy, the faster the reaction is. Now, remember, and which means the faster the rate. So this might be at the beginning of the reaction, where it has a really fast rate, but the rate might slow down at the end because when we slow down, we're not going to have as many of these available, so our rate will decrease the further we go in our reaction. So if we looked at the rate of our reaction, it will go like this. And this is lots of reactant molecules. So it's easier for them to react. And here, we don't have as many reactant molecules. So the reaction itself will slow down. Okay, last piece for today is going to be an endothermic reaction, which you probably learned about, hopefully, in biology. An endothermic reaction, the reactants have more energy, or the products have more energy than the products. So now if we look at our activation energy, it's huge, right? And this reaction is going to be much slower because the activation energy is so great. So if we look at the difference again, if we call this 10, and this 20. The difference here is positive, and this is endothermic. So when the products have more energy than the reactants, we have an endothermic reaction. When the products have less energy than the reactants, it's an exothermic reaction. And so these are, again, what we call reaction profiles. When we're looking at the activation energy, the bigger the activation energy, the slower the reaction. I guess the smaller the rate would be. Can't really do that with an arrow. It doesn't really decrease. It's just a small rate of the reaction, a slow rate. Okay, and the smaller the activation energy, the faster the rate of the reaction. Okay, so that was our introduction to kinetics. I highly, highly suggest that you, before we have our next lecture, look at the next section because it's a doozy. We're going to look at how we do this experimentally. You'll definitely need a calculator. We're not going to have lecture on Tuesday because the lecture is really difficult and I want your brains to be fully intact for when you take your exam, because your exam again is due next Tuesday at midnight. So those of you who haven't finished the homework, you need to make sure you finish the homework and take your exam. Start at no later than 9 on Tuesday. And so we're not going to have lecture Tuesday, but we'll finish and we'll not finish. We'll continue with kinetics on Thursday of next week. Are there any questions before we go on anything? No questions? Oh, what's the correct orientation? So the correct orientation means that so it has to be the correct orientation where they can react with each other. So if you had, usually what I use is my hand. So if you have like a reaction, something that looks like this, let's do like a Pac-Man. That's okay, that's a Pac-Man. So here's reactant molecule A. And here's reactant molecule B. The only way these two can react is if B hits A right there. If the orientation of B and A are in such a way where they hit each other right here, they will react. If B hits A over here, nothing happens. It's not the correct orientation. The reaction cannot occur. So that's what we mean by correct orientation. Both the molecules have to be positioned in such a way that when they do hit each other, they are able to react. Again, this reaction would not produce a reaction because if they're hitting in the incorrect orientation. Okay, any other questions? Any others? Okay. All right, so that's all for today. We'll see each other again this time on Thursday of next week. Make sure you watch the supplemental videos. They're very helpful. They're already up for you under kinetics.